Hello everybody, this is Darmus. I want to show you how to calculate G values, gravitational constant of every element. So the basis of all the G values is the G value of hydrogen. So for hydrogen, you divide the inertial mass by the gravitational mass. For all the others, you divide the gravitational mass through the inertial mass. So now, how do you distinguish them? For the inertial mass, you basically just take the atomic mass of every isotope and you multiply it with the percentage, with the abundance in nature. How much is there of each isotope? This is 91%, almost 92% of this isotope. And then for the gravitational mass, you simply multiply the number of protons with the atomic mass of the proton, and then you add to that the number of neutrons multiplied with the atomic mass of the neutron. And then you multiply that with the abundance in nature. And you add that all up. So you get here 56 point something and here 55 point. So this is hydrogen, but here we see things about iron. That's because we have to calculate out all the binding energy from iron to get to hydrogen, to get down to hydrogen. You see hydrogen is here very low, and this is iron here at the top. So everything that is heavier than iron, it drops again, the gravitational constant drops down again. And before calculating this, I thought, oh, maybe there's some amazing material, which maybe an artificial material which drops below lithium here. This is lithium. This is helium. This is lithium. This is beryllium and boron. So these are the lowest values. So here we can see all the different values, germanium and what's the heaviest? So organeson. These exist for fractions of a second. So the lowest ones are here. We can check 6.61. We get only hydrogen, and then the next what is the next lowest? I think it's here's helium 6.66, then lithium 6.65. So these are the lowest. After that it becomes pretty high. Carbon, these are still low. But most of the materials are pretty similar to each other, and that's why people don't notice that the gravitational constant depends on the material, because so many are so close to the gravitational constant of iron. Yeah. I want to show you an experiment with a boron cube and a silicon cube. This is a smart timer, and it's a free fall adapter with 2 photogates. And now I fix the boron onto this clamp here, and then I press this button here, and then I release it. Okay, it must. I think this is. Okay, 5923. So it took boron a long time to drop. 5923. And now silicon. 5873. 5910. 5850. 6138. Okay, 5859. 5859. 5881. 895. 5853. 5816. 5888. Silicon 5880. 5893. 584. 5905. Average. Deviation. We have this very irregular one here, so the standard deviation is quite large, but we could delete it, and it's a very large standard deviation. So the difference is this minus this. Okay. This is a boron cube and this is a silicon cube. Boron has one of the lowest gravitational constants, and silicon has almost exactly the same density as boron. So we expect that from a height of 32 meters, the volume difference in height should be about 5 centimeters. So let's try it.